current to DC current,
So this
and
is
how
a
the DC link bus section
inverter,
filters
DC
voltage
to
pulses
AC.
and
This
current
is
pulses
rectifier.
and stores
AC to
energy.
DC.
We need to spend some time and learn how the inverter section
So
works.
this is the inverter.
The inverter section uses what's called insulated gate bipolar transistors
is
to convert
IGBT.
DC current to AC current.
DC
It's important to
AC.
understand because there will be references to IGBTs
So
when you
for
are
IGBT,
troubleshooting variable frequency drives. I now have the variable frequency drive power component circuit open in multisim, and I'm going
how
to
can we do
simulate
it? We use
the inverter
carrier.
in run
With
mode.
the
And you'll see
sinusoid.
the output waveforms. I have removed the motor and I have 3 oscilloscopes connected. And I had to do that because it gets really busy trying to view it on a 3-channel scope. It's very hard to distinguish each waveform. Now, in the inverter section, we have 3 sets of transistors and they work together.
So 3 legs.
IGBT1
2, 3.
and IGBT2 are tied together. The emitter on
This is A phase.
transistor 1
B phase. C
connects
phase.
to the collector on transistor 2. If both of these transistors were on at the same time, you would have a short across the DC bus and you would have some serious issues going on.
If these 2
So we have
are
a
short
controller
circuit,
that only allows one of them to be on at any given
if and
time.
only if one switch
As a
is
matter of
turned
fact,
on.
if one is on, the other is off.
So one is on,
If the other is
another is
on,
off.
The opposite one is off. So they're always toggling. Just think of transistor 1 and transistor 2 toggling on and off. That is controlled by this driver circuit right here. It's
This
called
is
a
a
pulse
driver.
width modulation
But
3-phase
with modulation,
sinusoidal driver. It
sinusoidal.
tries to replicate the AC output
so it converts
at the inverter leads that connect to
AC
the
output.
motor. These 2 leads toggle. P1 and not P1 are always switching back and forth in their
So
pre-time
we cannot
sequence.
turn on
The same
together.
for
Only
P2
one can turn
and
on.
not P2 and P3 and not P3. So we call it phase 1 control, phase
Phase
2
1,
control, and phase
phase
3
2,
control.
phase 3, A phase, B
Now, if I
phase,
open
C
this
phase.
up, there's a box that allows us to make adjustments. We can change the switching frequency. It's called the reference frequency, but if you were
Reference
programming on the drive, it would be called
Carrier
the,
frequency.
switching frequency or carrier
Or
frequency.
switching
I can
frequency.
change the speed
Carrier
from 60 hertz to 30 hertz using the modulation frequency.
So we
we'll do
use
some of that.
modulation.
Okay, so I'm going to zoom out and we'll do a quick power flow through the transistors. And we'll just do one because otherwise it's going to take forever. The same thing would happen, what I'm going to show you now, the power flow will happen with the other 3 transistors, we'll say. So power will flow if IGBT T1 is turned on.
If
Power will
T1 is
flow
turned
to
on,
the collector emitter lead.
then we can have a
It will
current
flow onto
go here
T1 out to the motor.
to the motor,
Some current will come back
then
on T2.
go back to B phase,
Now there is overlap with 3
And
phases,
go here,
and some current will
return.
come back on
so
T3.
from here to motor
It'll
to
come
B phase
through
to negative,
BT4 onto the DC bus, back
And
to the
then go
supply. And some current will come through
so
on
also go from A to
IGBT6
C and
and
go
then back
back.
to the supply. And then one
So,
of them will shut
1,
off, and then a little
0,
current will
0.
continue to flow on the other one, and so on. So they sequence in 3s. So just keep that in mind.
So we call this 1,
That's
0,
how it works.
0.
Okay, so what I'll do now is I will run the oscilloscopes. And
So you can see the waveform here. Okay. So the waveform is not a square. It is with modulation.
At the output,
Before we
you
have
can
this
zoom
line
in,
of
you will see that there's
waveform, but now we have
pulses
pulse with
of
modulation.
or slices of voltage. And the controller, the sinusoidal controller, creates this PWM.
So PWM
of those pulses
with
determines the
modulation.
average voltage that's applied to the motor stator leads. If you were to measure each one of those and plot those values on a chart or on some graph paper, they would end up looking similar to an AC waveform.
So it is similar to
Now,
AC,
notice that they don't
but
line
not
up
pure
face
AC.
each other.
Only similar, but not real
So the
AC.
starting point of each square vertical waveform pulses, we'll say, are out of phase by 120 degrees
So the
each.
phase shift
That's why I couldn't put it all on one
120
screen, because you would see so much overlap, you wouldn't be able to see each waveform.
So
each
B
motor
leg A,
sees
C leg B,
these pulse width modulated output
with
waveforms.
modulation waveform.
Now, right now, we are running at 60 hertz.
So
what
now
I
this
will
is 60
do,
hertz.
I will slow the motor down. I haven't tried speeding it up yet. I'll take it down to 30 hertz and you're
So
going
30
to
hertz.
different looking waveform.
So change from 60 hertz
I've slowed
to
it down.
30 hertz.
Now we're controlling
So you can see this become
the
wider.
output at a slower frequency.
So
So
now
on the
it's
same
30 hertz.
oscilloscope screen, you're going to have less alternations. You're going to have half the alternations of what
So
you
the
had at
frequency
60
becomes
hertz.
half.
I can try to
Time
take it
interval
up to
become larger,
to 120.
become twice.
I haven't done that yet. We'll see if the simulation can handle it. So now we're gonna take it up super fast. 1, 2, 0.
1 to
Hopefully you
0
can handle it.
hertz. So become twice.
I have to stop it and restart it.
So you can see become twice. Then
Now we should see a lot of
time
alternations. Now
period
the motor
becomes
is running
shorter.
Twice
because
base-
the frequency
basically
become
with
twice.
60 hertz, now we're running at 120 hertz.
120 hertz.
One more thing we can do is we can adjust the carrier frequency.
So we also can adjust carrier frequency.
So I'll stop it. And the carrier frequency will determine how many bars are produced.
Determine how
to
many
replicate that
pulses.
waveform. I'll change it. I'll take it down to 1 kilohertz.
So now it's 1
That's
kilohertz.
okay. You might not see a big difference in that case.
Carrier frequency
Now, this
reduced.
is like
So you
a-
can see
So that's a, that would be
pulse
an
number
easy-
reduced.
It's a lot easier on the motor, but you can certainly see the pulse width
So we
modulation.
can reduce the
that's used
switching
to,
frequency.
recreate that AC waveform. What I'll do now is I'll just take that up to 16 kilohertz.
So now it is
I think
16
it's going to slow down the
kilohertz.
simulation quite a bit.
16 kilohertz is quite
It's a
high.
lot of work for it.
So you can see
Each one of those is turning on
You
and off
cannot
16,000
identify
times a second.
the pulses
to create
because
that
it
AC.
is
So when you
weak.
set the carrier frequency on an inverter drive to
The
16
pulse is too
kilohertz,
small.
it's basically what you're seeing at the output. Very, very fast switching. It's
So
actually harder on
It
the
is too
drive.
quick. You cannot identify
Okay, so I'll
each
just set it
pulse.
back. I'll set it back down to 2.
So now it's
And
2
then we'll balance
kilohertz.
up.
So it is quite slow. 2 kilohertz. You
There
can
you go.
see
So that's what you see on
the
the output
pulses.
of the drive. So when you're measuring these things, you have to take that into account. If you've got one of your transistors blown out, you're going to see a problem when you're troubleshooting. They talk about testing the IGBTs or having a short circuit fault at the IGBTs. They're talking about the output transistors that connect directly to the motor leads. And they are in the inverter section.
Okay, so this is the first part. The first part that introduces the PWM pulse width modulation. And then we will see the second video about drive. So this is a Japanese company, Yasakawa.
The Technical Training Department of Yaskawa America Incorporated presents variable frequency drive.
Variable frequency drive.
Have you ever thought about what goes on inside a variable frequency drive? After all, when we stop and think about it, these mysterious boxes
this is
are really
inverter.
remarkable. They help us save energy, reduce
Saving
maintenance
energy.
on our machines,
Because
and
it can
give us
adjust the
infinite
motor
control over
speed.
almost any type of process powered by a three-phase.
So this is fan.
So how exactly do variable frequency drives, or VFDs, work? And what do you need to know about them? I'm Steve Kaler. Welcome to the second video of our two-part series on motors and drives.
Motors
In part
and
one,
drives.
we were introduced to the basics of three-phase AC electrical
So
motors.
three-phase AC
Today, we're
motor.
going to look at the basics of VFDs, or
So variable frequency drive.
You may also know them as adjustable speed drives, adjustable frequency drives,
adjustable speed drive.
and inverters. Whatever you call them, what's important is what goes on inside of them and how we use them to control and monitor electric motors. In this presentation, before we look inside of a drive, we'll start with the many applications for variable speed drives.
So what kind of
We'll
applications
look at other
for
starter
motor drive?
ways to start a motor that don't utilize a drive. And next we'll talk about the purpose of variable speed drives, why do we use them,
So when we need to change frequency.
and construction of a drive, and explain the components that make up this device. We'll look at different types of enclosures, and then to wrap things up, we'll review this presentation with a few questions.
So for some applications,
Now, before we look at the inner workings of a drive, let's examine the applications that could benefit from a drive. Industrial applications often require very precise control. In past, these
Precise
applications
control.
required complicated gearing and clutches to control
before
the
we use
speed of the
gears,
system.
gearing,
Examples would include conveyors,
conveyors,
cranes and hoists, presses,
presses,
winders and unwinders,
winders for
high-speed
motor.
machining applications, as well as many others.
So many
Now,
applications.
in the commercial market, we are normally trying to achieve a given flow and pressure.
Flow
This
and
changes
pressure.
depending on the demand at any given time.
like
Fans
fan.
use inlet guide vanes, bypass dampers, or outlet dampers for flow control.
So for
Pumps use
wind flow
discharge
control.
valves or bypass valves to regulate pressure. Cooling towers use a
Cooling.
mixture of the two. Using a variable frequency drive for these types of industrial and commercial application allows us to remove mechanical speed, flow, and pressure control systems that may prove difficult to regulate and could possibly be failure points. Instead, the drive easily adjusts speed and torque to given system demands.
So we can adjust the speed and the torque.
Some variable torque commercial applications can take advantage of affinity laws and use the least amount
So
of
we can
energy
do
to meet
energy saving.
or pressure demand. This can lead to energy savings that can have the drive system paying for itself within a short period of time. As we explained in motor basics,
So this is a three-phase induction
motors
motor.
are applied across the line, run in a narrow speed range, depending on load and motor characteristics. On their own, they're either on or off.
Before we only
Motor drive
control
systems
on
are
or
often
off.
incorporated to allow the system to operate at a wide range of speeds while still producing full load torque if needed.
So we need full load torque.
The simplest form of control is a manual motor start.
So before we use mechanical,
Manually open and
we use
close
menu,
contacts
use
to
man
start
to
and
turn
stop the
on,
motor.
turn off.
Manual motor starters usually include some type of motor
On and
overload
off.
protection. A magnetic motor
Then we
starter
use a
is
delay.
similar to a
This
manual
is a
starter,
delay.
Except you can
We control the
open
delay, turn on
magnetic
and turn off.
to bring in the contacts.
So stop.
A drawback to both manual and magnetic motor starters is that they do not reduce
So they
the
have inrush current.
experience at startup. Primary resistor starting uses
So then we
resistors
use
to reduce the
resistance
voltage in the motor.
to limit
After a
the
given
starting
time, resistors
current.
are bypassed and full voltage is then applied to the motor. These resistors will get hot.
But it will get hot.
Cycle. In other
And
words,
then it creates loss.
start-stops in a given period applies. With auto
And
transformer
we use
starting,
auto transformer starting.
at different
We
points.
can change
This
the
is
voltage
change in
of the transformer.
After the motor is started, the transformer is bypassed. With Y delta
And we
starting,
also
we
use
connect
Y
the
delta
start in a
start at Y,
which
and then
exposes each coil to
steady
low
state
voltage,
move to
then
delta.
switches over to delta while the motor is
So
in
we
the
call
state.
Y delta starting.
SCR.
And then we use SCR, Syristor, silicon control rectifier, to control the motor.
These offer a smooth start to the given system and limit the current draw by the motor. When the motor is up to full speed, the unit then bypasses the soft start function and full voltage is applied. These units have limited start allowances for a given time period, but offer smooth starts instead of the stepped previous one.
So now we need smooth
So
start.
that
So
brings
we
us to
use
the purpose
variable
of
frequency drive.
Here are some of the major capabilities a drive provides. If you viewed the motor-based
So this is a
you saw
induction motor
this diagram
torque.
showing
curve.
the induction motor's relationship between speed and torque.
So this
By
is a
adding
speed,
drive
this
to the
is
system,
torque.
we have the ability to alter the speed-torque curve. This lets us take advantage of the motor's characteristics at multiple speeds instead of
So now
limited
we
to-
change the frequency. We can keep,
VFD allow
a
us to
full
match
load.
the speed of the motor-driven equipment.
but we need
to
to
the
change
load
the
requirement.
frequency.
Operating a motor with a VFD provides full torque
Full torque
over a
capability
wide range of frequencies.
And the wide
Having
range.
full torque available allows us to use a standard
So
or
you
general
can
purpose
see
motor
this
in
application,
many more
cut
applications
wood.
and situations than we would otherwise be able to. Furthermore, we can limit the output torque of a motor for a given application or point.
So
in the
we also
process.
can limit output torque.
Since we now can control the motor, we
Like
can
this.
program our own acceleration and deceleration.
So we can control
or
the speed.
Accel and decel times. Now this will
So
vary
you can
depending
control
on the application.
precisely.
For example, a fan can utilize longer accel and decel times, so the motor draws a low amount of current, reducing energy consumption and associated belt wear. On the other hand, some industrial
Yes, sir.
applications require fast response.
Fast
This calls
response,
for very
quick
short
response.
accel and decel times.
Yeah, very quick
Built-in motor protection eliminates the need for external motor protection. In
protection.
variable torque applications,
And we
some of
have
this can be seen due to the
variable
affinity laws. A
frequency.
small reduction in speed can lead to a dramatic decrease in power usage.
So we can
You
set
can have
power.
a torque at zero speed
So you
to
can see this
hold or
one very
lock the
quick.
rotor, a feature
Yeah, very
previously
quick.
limited to servos and mechanical
This
brakes.
is servo.
On the
very
other
quick
side of the
and
table, you can
precise.
now overspeed and run at speeds above 60 Hertz, provided the motor is able to
But we
accommodate
need
that speed.
high torque.
Remote monitor control means that you can monitor and control the system from your desk
So
or
we
from
can
anywhere in the
monitor
world
and
where you
control.
have an internet connection. We are now going to explain how this device actually works. Now, as we go through, each component will explain what it's doing and how. Together, the components make a three-phase electrical
Three-phase electrical motor.
usable work.
And change
With
frequency.
three major drive components.
So we call drive components,
Power.
control,
And the main
power,
circuit.
main
We'll
circuit.
start with control.
So we
For
start from
most drives,
control
the operator uses a digital keypad
So this
to
is a
program the
digital
unit for the given
pen
application.
to
And in
control
some cases,
the frequency.
operate the drive locally via the keypad. Things like overloads, accel and decel rates, minimum and maximum
Acceleration,
speed, and many other
deceleration,
parameters can
minimum,
all be
maximum
set through
speed.
the keypad. For a user looking for some more advanced setups,
So you
there
can
are
see a lot of
options that can be
circuit,
added, which
a
include
lot of
communication
circuit
options,
inside
feedback encoders, and extended
Encoder
inputs and outputs.
and
For
feedback.
controlling purposes, the user can wire into the digital
we can
inputs and
control.
outputs.
We can
and
use
analog
DSP
inputs and
to
outputs.
control the
The
motor.
I/O terminals also support some communication protocols. Finally, we get to the control board.
Control
Now, think
board.
of this like the brain for the drive.
This is the brain of the drive.
And drive components, and relays the given information or task.
So you can see DSP, a lot of circuit.
Let's look at the selectable control methods the drive comes with. These different methods are
So,
programmed
the first
by the
one is
operator into the control
Variable
board.
voltage
Depending
frequency.
on your applications and needs, you will want to choose the control method that
Open
best
loop
fits your
vector,
requirements.
closed loop
As we
vector,
move through each of these methods, control becomes better and better.
and in general we use
Or
PM,
voltage by frequency
permanent
control is
magnet.
the simplest method.
This
So
is
follows a set
constant
pattern,
voltage
increasing
frequency
voltage as
control.
frequency increases.
So the voltage is proportional to frequency.
It's also very good for applications that do not need tight speed regulation of the motor. When adding a pulse generator or PG feedback device,
So
the
this is
speed regulation becomes
pulse
higher.
generator
The drive
to
actually
provide
knows
the speed
and
operation
direction of the
signal.
motor. A PG is commonly referred to as an encoder.
Encoder, it is an
Open
encoder.
loop vector control is a step up from VF and is great for dynamic motor
Open
control.
loop
And
vector
can produce
control.
higher torque levels at lower frequencies. This method can also limit torque output. It's great for conveyors and most other
Conveyors
general industrial
And
applications.
industry
Closed
application.
loop vector control uses
So
an
now we
encoder
use
or
closed
PG
loop
to
vector
give
control.
instantaneous feedback to the drive. This allows the drive to be used in true torque
True
control.
torque control.
This is great for winders,
So
rewinders,
this is quite
and web
very
applications.
precise.
Zero
high
speed motor
performance,
control is
zero
also
speed.
possible. Control methods available for PM or permanent magnet motors may also
Permanent
be
magnet motor.
This motor is similar to the induction motor we talked about before, except the rotor now incorporates magnets
So we
to
use
create
permanent
magnetic
magnet.
field instead of the typical shorted rotor bars. Moving from the control side deeper into the drive, we find ourselves
this is
at the main
drive.
power board.
This is the main
separates
power
high
board.
and low voltage areas, converting signal levels to something the control board can read and output to. This is used for monitoring critical areas of the drive as well as controlling them.
So this is a power stage.
Is where all the heavy lifting
This is a bus bar. You
The
can
heavy
see
transformation
couple bar.
Most drives now use the same main
So this
circuit
is
with a three-phase
rectified,
DC
AC to
source
DC.
that is converted into DC.
So AC to
and back
DC
to
rectified,
simulated AC.
and a DC to AC inverter.
Let's start by moving our way from left to right, building our drive, and understanding the components along the way. Starting at the input of the
So
drive,
this
the
is
first
AC to
device in the
DC.
incoming line will
You can see this
MOVs, or metal oxide
Varistor.
resistors.
To get the surge voltage. Otherwise you will be damaged easily. So they use this one to take away the voltage surge or spike.
Resistors come into contact with a high spike.
High
They allow
spike.
the spike to bleed off to another line and travel safely back out to the incoming line. Thus,
like this.
suppressing the spike and protecting the more expensive components in the drive. Well, this brings us to the input diodes, or
So this
input
is
converter.
input diode.
Or
1, 2, 3, 4, 5, 6. AC to DC.
Most drives
So
today
input is
form a
AC.
full wave
Then we convert into DC.
which means these
So
diodes
it
trap
convert
the
AC
line
to
and
DC.
create DC supply. That is the first of the three major components in the drive. The voltage
Then we
output
use
from the rectifier
capacitor
is then
as filter.
defined by a filter
So this is capacitor.
large capacitors, and in some
And a
cases,
large
DC
inductance,
choke.
LC filter.
In any system using a combination of a rectifier and a filter, capacitors may result in discontinuous
So-
current draw.
The capacitor is
Results
too
in
huge.
harmonics being reflected back on the incoming line. Yaskawa has a video titled Harmonics that further explains this topic and ways to mitigate harmonics. The components between the rectifier and the filter capacitors comprise a soft charge circuit. When you apply power to the drive, the unit must safely power up.
So when you have surge, go this way,
You must slowly charge the
reduce
capacitor to the
the
drive.
surge
An
current.
uncharged capacitor will act like a short if full voltage is applied to it instantly. This is not desirable because the inrush current may be
Otherwise
too
you
high
have
for the
inrush
rectifier and
current.
upstream supply components. Therefore, we use a soft charge circuit to slowly charge
So
the
we
capacitor.
use soft
Soft
charge.
charge
We
circuit
use
is made up
resistance
of
to
contact
limit
and
the
a
current.
resistor. Now the resistor limits the current
So
flowing to the
resistor limit
after
the
the
current.
charges. The contactor closes and bypasses
So
the resistor.
after the transit, we can close the switch.
Most of us will follow the path of least resistance. Once the DC bus capacitors are charged, they act like a storage tank
So
for the drive.
this is like a storage
Stores
tank.
voltage for the system. These capacitors also have a smoothing effect for
So
rectifying
it is
power.
filtered,
This
smoothing.
smoothing reduces
DC
peaks and
voltage.
valleys of the three-phase
Before it
power
is
that has been
ripple,
rectified.
now it is
This
smoothing,
reduction in ripple helps reduce the wear on the
reduce
system.
the ripple.
It's also important to note that the voltage level in the drive has now changed by rectifying AC power. The new DC bus voltage can be calculated using
So
this
we
formula.
can use this
V
to
DC
calculate
equals
the
the
DC
square root of
voltage.
2
So
times
you
the
have
voltage of the
AC,
incoming
you
AC.
can calculate the DC.
We now move to the last major section of the drive, the output, or more specifically,
Inverter
the
here.
inverter section. The
DC
inverter
to
section of
AC,
the drive is comprised of
inverter.
IGBTs,
So
which stands for
you can see
insulated
the control board.
bipolar transistors. These
IGBT.
work together to produce
So
a
the
steady
waveform is like this.
AC waveform to the motor. One IGBT
So it is like
power
this,
to build
not a square
the
wave. It is PWM, pulse width modulation.
Then another IGBT building the lower half of the wave. Now remember,
So you
we
can
have a
see the
three-phase
waveform.
motor. So typically, 3 IGBTs are on at a given time to generate simulated AC
So we
voltage
can
waveforms
generate
to the
this
motor.
waveform.
These IGBTs have built-in diodes that allow current to
We call
flow in
this
the opposite
RD
direction
diode
of the current
inside
flowing through the
IGBT.
IGBTs as may be
Or
encountered
we call
when
this
turning the
free
IGBT
feeling
off
diode.
or when exposed to
Free
regenerative
feeling diode.
currents. However, the rectifier blocks the regenerative energy
But
from flowing
our
back
energy
onto the
cannot
line.
go back because of
This is
rectifier.
also one reason why
blockade.
you might encounter an over-voltage trip. Yaskawa does offer systems that have the
So
ability to put
they
power
mention
back
about
onto
the
line.
matrix converter.
These units use different
AC
drive
to AC.
topologies that allow for regeneration.
So regeneration.
After the IGBTs come the DCCTs, or direct current to current transformers. The DCCTs monitor output current
So we have
on all three
sensor
phases of the
monitor
motor.
the current.
This can be used for control and motor protection.
So here, yeah.
Let's explain how these IGBTs work together to build this three-phase power.
Three-phase power,
The
IGBT.
IGBTs are controlled using PWM.
So PWM
and
control the
pulse width
IGBT. You
modulation.
can see this waveform.
The IGBTs
Like this.
are basically switches that work at a
So they
very
switch.
fast rate.
Change
They are either
the pulse
on
width.
or off.
And then here are sensory waveform.
Time they are on or off. So, to build this waveform.
So it is close to
we
sensory.
stay on for a very short
Like
period
this.
of time. Then we increase our on time relative to the base sine wave we are building from. After reaching the peak, we
So
then
this
start to
is
reduce
small
on time
turn-on duty,
until the
then
0 point
small
when another
turn-on duty.
IGBT starts to
So
turn
it
on
is
to
like a
create
sinusoid.
an inverted wave. You will notice that the voltage waveform is almost square, but is happening in the positive and
Positive,
regions.
negative.
And that's because the IGBTs are pulling from the constant DC bus. Voltage reacts very quickly,
So very quick.
which causes this block-type output. The pulses are high in amplitude, but the RMS or root mean square voltage appears equivalent to the motor-rated voltage. You will find motors that can handle this PWM style waveform tend to be labeled inverter duty on the nameplate.
So inverter duty.
Now the rate at which
Turn on, turn on,
IGBT
turn on,
switching
turn on.
occurs is known
And
as
then
the
we
carrier
add this
rate.
waveform. Very similar to sine wave.
Frequency can be adjusted if need be.
So we call this is carrier.
Increasing the carrier will result in a cleaner, more sinusoidal current waveform.
More sinusoidal
which in turn
waveform.
will make the motor
Reduce
generate
the
less
harmonics.
audible noise. However,
Less
it will also
noise.
make the IGBTs work hard and create
IGBT
more
work
heat
harder.
in the drive.
And create
It
heat.
may be necessary to derate the output current of the drive to accommodate for the increased carrier frequency.
So if increase the carrier, then the loss become increased.
Louder when connected to a drive versus across the line is due to this switching frequency. The stator laminations in the motor vibrate, causing this audible noise.
audible
Increasing the
noise.
carrier only brings that vibrating frequency to a level that becomes difficult for us to hear.
So difficult to hear. You cannot hear the acoustic.
Decreasing the carrier will lead to the opposite characteristics.
So
That
if
is,
you reduce the
more
carrier, you
noise,
can
but
hear
IGBTs
the
don't have to work as hard.
noise,
As a
the
result,
noise come from motor and the inverter and the
You
cooling.
can see how the fundamental output
So
frequency
this is
reference in
the
blue
output voltage.
reflects onto the actual output.
So it
via
is
the
close to
superconducting
sensoric.
frequency. Well, we are finally
So this
watching
is the
output current
current.
for a given phase.
Very
As you can
close
see,
to a sinusoid, but a
sinusoid.
lot of
Well,
harmonics.
remember that an induction motor is basically an elaborate inductor. And what do inductors mainly care about? That's right, current.
Current.
Well, the drive is sending the motor a relatively nice and clean sine wave so it can do its job, which is to turn shaft and produce work. Well, now that we've walked through the inner workings of a variable frequency drive, let's head to the lab and take a look at the outside of the box.
So
You'll
they
find
show
information about
inverter
each
to
drive
you.
on its nameplate.
They
The
open
front cover has information such
the
as the
cover.
model number and serial number, which you would need if you ever have to contact tech support. You'll also see
So
the
you have
voltage
number.
class and the amp rating in normal and heavy-duty situations.
Yeah, this is
On the side
ampere
of the drive, you will see the full nameplate with all ratings and certifications.
ratings.
Depending on the type of environment the system will be exposed to, the drive enclosures will vary. NEMA 1 enclosures are designed for indoor applications.
This is
and provide
indoor
protection against
applications.
contact with live electrical components.
Put
and a
indoor,
limited amount
not
of
outside door.
debris. NEMA 12 steps up the protection. It's
Protection.
also designed for indoor applications.
This is
And
indoor.
all openings have filters that require regular maintenance. The filters protect against circulating dust, falling dirt, and non-corrosive dripping water. NEMA 4X enclosures are designed both for indoor and outdoor applications and provide a degree of protection against falling rain, hose-directed
Raining
water, and
water.
damage from ice formation. NEMA 4X also provides protection against corrosion. Let's head outside and take a look at a NEMA 3R.
Okay, you can
NEMA
see.
3R enclosures are designed for outdoor applications.
This is
They
outdoor.
provide protection
Snow.
against falling rain, sleet, snowball,
Snowball.
and prevent corrosion
Raining.
from the formation of ice on the enclosure.
So it
Rain
endure
hoods
raining
over the
and
ventilation
the
holes
snow.
prevent rain and insects from entering the cabinet. Yaskawa 3R enclosures also include filters
Filters.
to provide some protection against the
So this
ingress
is
of
a
dust and
protection.
dirt, which is not a requirement for UL or NEMA specifications. And now it's time for your favorite part of our program, the review questions. Number 1, does a motor draw more current when started across the line or when started using
So
a
which
vehicle?
one get more current?
When starting a motor across the line, there will be an inrush of current.
If you
This
do not
is due
use
to an
inverter,
instant frequency of
you
60
get more
hertz applied to the
inrush
stator
current.
at full line voltage, and the rotor must
The inverter can save
That in
energy.
turn causes excessive current draw. The drive has the ability to slowly increase frequency and
So
voltage.
drive
owing to
have
the
the
motor
ability
thus
to slowly increase frequency.
Question number 2. What does the acronym MOV
What it does
stand for?
MOV,
That's right. Metal oxide
metal oxide
resistor.
very
These
special.
help dissipate some high
To
incoming
get the
voltage
high voltage
that could
surge
damage the internal VFD components.
for protection.
Question number 3. Does a drive output a purely sinusoidal
Can we
AC
create a
voltage?
pure sinusoidal AC waveform?
No. The
No.
drive outputs a simulated
Only
AC wave
similar,
that uses
but
PWM
not a
or
real
pulse
AC.
width modulation to build the waveform. And now for our final question. Can a drive be mounted outdoors? Well, of course it can be.
So
It's
yes,
enclosed in a NEMA 3R cabinet. A 3R cabinet is made to withstand rain and sleet.
rain and snow.
Well, this program is just a basic
So this is
introduction
a
to
basic
variable
introduction.
frequency drives. What
What
they do
is
and
the
how they
variable speed
There's
drive?
a lot more to learn, and a good place to do that is at Yaskawa.com. Yaskawa gives you a high standard of product excellence, high mean time between failures, low cost of ownership, quick response to your questions, free technical support 24/7, and a great return on your investment. You get it all from Yaskawa, the world's largest manufacturer of AC drives and motion control products. At Yaskawa, we do everything we do to make each experience with us a great one. Thanks to us.
So we watched two videos. One is about inverter. One is PWM inverter. The second is about AC drive. So what is the purpose for inverter to drive AC motor? So we will discuss in details for this new chapter. So we call DC to AC converter. So now we will move to the sixth step. So what is the advantage of sixth step inverter? It is easy to understand. What is the disadvantage of the sixth step voltage source inverter? The first thing is harmonics are too huge, right? And the harmonics are low order harmonics, fifth harmonics, 7 harmonics, 11 harmonics, 13 harmonics. So it creates a lot of current. So this is the disadvantage of the sixth step voltage source inverter. So if we check the harmonics, the third harmonics can cancel. But how about the fifth harmonics? We have fifth harmonics. How many percentage? 20%. So if you have fundamental 100, this is 20. So it is too huge. How about the 7 harmonics? 114%. So 7th of the fundamental. So if we use the sixth step voltage, the disadvantage is the harmonics is too huge, right? So how can we solve this problem? So you can see this one. So the only way we can use increase frequency, right? So how can we increase frequency? So for a motor, you have 60 Hertz. And then before, you say we can use the line voltage, which is 60 Hertz. So we have this one, 16.6 milliseconds. Then we can create 60 Hertz. And now we want to push the waveform become higher frequency. So we need a higher frequency. So why do we need high frequency? So how can we create high frequency? So before maybe 50 years ago, some people say, oh, this is not good. We needed to increase the frequency, become higher. But how can we create high frequency? What is the logic? What is the method? What is the algorithm to create high frequency? So people learn from communication. So we have communication technology. So if this is Taipei, and this is Taichung, and you want to make a phone call, so you have a line, telephone line. So you call from Taipei to Taichung. Can you use this line to call your friend? So you have a line, you get a line from your home to your friend's home, and then use your telephone to call your friends. Can your friends talk with you? The answer is no, because it is too long. So if you make a phone call, maybe your voice is only maybe 4 kilohertz. So 4 kHz, maybe you can call from this door to another building. So then it is okay. But if you want to call from Taipei to Taichung, then your friend cannot hear because the distance is too long. So in general, our frequency is related to the communication distance. If your distance becomes longer, then you need a carrier. What is carrier? So if this is your voice, so your voice comes to the telephone, then you need to generate carrier to increase your frequency. So the carrier could be like this. So it could be 100 times, 1,000 times of your voice. Then we can get a high frequency. After the high frequency, we can transfer the message to Taichung. And then your friend can get the message. However, you have to remove the carrier before he can hear, right? So we call this is modulation. We add carrier, and then we have to deep modulation. You remove the carrier, and then you can get the voice. So we need this kind of technique for communication. So in general, we call this is carrier technology. So people found that this is a useful way to use a long distance to have a long distance call before we have wireless. So they think this could be applied for power electronics. So they say if I have a sinusoid waveform, or if I have a square waveform, if I need to increase the frequency, the only way is I have to put carrier and change the switching pattern. So this is a good idea. So we can use a carrier to change the frequency. Because the carrier is high frequency, so we can push our switching frequency to kilohertz, 10 kilohertz. So this is a good way. So how can you select carrier? If you need carrier, what kind of waveform is better? So first, people think we could use this, like this, right? So, and then another people say maybe we can use triangular. So which one is better? Sawtooth or triangular? So if you think triangular is better, please raise your hand. If you choose sawtooth is better, please raise your hand. So which one is better? What is the difference? So from the math you can prove if you use this, then you create even harmonics and odd harmonics, both. If you use this, you can remove even harmonics. So you only have odd harmonics. So which one is better? Triangular. So in general, we use triangular as a carrier. We do not use sawtooth. This is sawtooth. This is not good because it creates odd harmonics and even harmonics, so the harmonics become double. So this is the reason people always choose triangular. So we choose triangular, and we put our sinusoidal waveform, and then we do pulse width modulation. So how can we decide the switch is on or off? Then you can see if the signal is larger than carrier, this one, signal is here, carrier is here. So signal is larger than carrier, then we turn on the upper switch. So we can get 0.5 VDC. Here, our singular is lower than the triangular. Then we can get the lower leg, so become minus 0.5 VDC, right? So we use comparison. So comparison is very easy. We can use operation amplifier. And we have two singular. One is carrier, another is sinusoidal. And we use the voltage comparison, and then we can generate high or low singular, right? Then we can get triggering singular. So we use operation amplifier to do the comparison. Then we set a rule. If the singular is higher than the triangular, then we turn on the upper switch. On the other hand, if the carrier is larger than singular, then we turn on the lower leg. So we can generate this one. This is higher than carrier, then positive 0.5 VDC. Here, carrier is higher than singular, then minus 0.5 VDC, right? So we can create this waveform. If we create this waveform, then what happens? You can see here, the positive is larger than negative. The duty of positive is larger than negative. Then the overall should be positive. Here, the negative is larger than positive, right? So the overall should be what? Negative. Here, positive and the negative, the width is equal. Then the voltage is equal to 0. So we can generate this waveform. So if you use Fourier series, you can prove if you create this waveform, then the majority is sine wave. So the theory is very easy. We just learn from communication expert. So we just apply it into the power electronics. Then it is easy. We can get sinusoidal fundamental. So the idea is very clear and very easy. So you will think, if I was born at that time, then I can get a PhD in 1 week. So easy, right? But now it is too late because people publish it. Then if you say I can use triangular to compare with sinusoidal, then people say, so what? Because everybody learns it, right? It is a kind of well-known technology. So it become, you cannot publish anything. So we have switching frequency. We have fundamental. So what is switching frequency? In here it will be 10 kilohertz. What is fundamental? We need 60 hertz sinusoidal. So we can compute this one to this one. So we can say 166. We call this is MF. So this is frequency modulation ratio. So do you think higher carrier is better or lower carrier is better? Which one is better? So 1 kilohertz is better or 10 kilohertz is better? Which one? If you think 1 kilohertz is better, please raise your hand. If you think 10 kilohertz is better, please raise your hand. So in theory, if we can increase the carrier, it is better because the ratio is larger, right? The ratio is larger. But what is the real situation? If you increase to 10 kilohertz, what is your switching loss? So do you think your switching loss will increase or decrease? Increase. Because you switch one time, you create one loss. If you create 10 kilohertz, you got a lot of switching loss. Then your power device become, temperature will become increased and then burn out. So you cannot push the power device to too high. carrier. So if I put the carrier to 1 kHz, is it good? Because I'm afraid of high temperature. I try to reduce the switching frequency and I push to 1 kHz. Do you think this is a good idea? Then what happened? You can hear 1 kHz clearly. Then you feel uncomfortable. And if you have a dog near the inverter and the driver, the dog will be crazy because his ear is more sensitive than human, so he cannot endure. So in this reason, we cannot set 1 kHz. We have to push to 10 kHz. Otherwise, your ear cannot endure. It creates noise. And what is the next problem? If you use 1 kHz, then your harmonics will increase. So higher carrier, small harmonics. So you have to push as high as possible. But from the physical point of view, you still have limitation. What is your limitation? Switch loss. And your device, some device is not so quick. So you cannot turn on, turn off, turn on, turn off. They cannot respond. So there are some limitations. So I think we can have 20 minutes break and we will go back.